Hello, my name is Julian Avellaneda.
And I'm Naum Pina, and this is our project on machine programming for computer architecture.
So what is machine programming? The basic definition is any technique which can automate hardware or software development. When we usually think of this sort of definition for machine programming, we think of GitHub Copilot, for the software side, code intelligence, helping us write certain functions or debug our code. But also for the hardware side, this is a pretty old article, but we can see here in 2021, an AI developed by Google was able to design computer chips in faster time than humans. So those are just two examples of machine programming, both with software and hardware. The relationship of machine programming, sometimes we think of it a lot like AI, which it has a lot of similarities, specifically with the machine learning and deep learning, which kind of intersects both of those big subjects. Other parts of machine programming that we usually think of are compilers and also just normal programming languages. If we look back at the definition, any technique that automates our software or hardware, compilers are able to take our high-level code and bring it down to machine code, kind of automating that process for us. And the same thing with programming languages. We don't want to type all of our programs in assembly or in, binary. So we use those high-level programs, which is able to automate that for us. How does machine programming work? This is a pretty basic diagram of how the kind of flow of the machine programming is done. We start off with data, big amount of data. Once we have that data set or group of data, we have to interpret that data. What does it mean? Is this right or wrong? Basically input to output. And that is what's going on behind the scenes. And with that interpretation of the data, the machine then has to make a decision. And it is the human's job to tell the computer if that decision is a success or a failure. That is the only way that the computer will know if the decision they made was right or wrong. So because of that, we can describe machine programming and how it works as a series of decisions in order to create a favorable outcome with the overall goal of improving programmer productivity. With a goal comes challenges. So we have some pretty big challenges when it comes to machine programming. The first one is big data. We need large data sets and a big amount of data to make the type of programs that can, actually automate software that we want to use. If we don't have enough data, our output is not going to be good enough or usable. If we have too much data, it might be too hard for us to interpret that data. We also need a lot of computational power. We can see here, very big looking PC with a lot of different parts that we normally wouldn't put in a computer, just because any sort of program that uses machine learning or machine programming, things like that, needs a lot more computational power. And a machine like this is built for machine programming. And then we have decision interpretation, which we kind of talked about earlier. It's kind of hard for a computer to know what's right or wrong. And it's also hard for us to decide if the decision the computer made was a success or a failure, especially with so many decisions that the computer can make. A brief history of machine programming. The first assembly language ever designed was in 1947 by Kathleen and Andrew Booth, called Coding for ARC. That was a pretty big step in the development of languages and machine programming. We also have in 1956 the first high-level language called Fortran. A lot of us has probably heard of that. That was developed by IBM. It's actually not listed here, but the next year we actually have the first commercially available compiler for Fortran, which was also a big step in machine programming. But probably the two most important, milestones in the history of machine programming came in 1957 and in 2006. In 1957, Frank Rosenblatt developed the algorithm called perceptron. which is a basic machine learning algorithm which uses neural networks that are still used today. And also in 2006, Geoffrey Hinton published his famous paper, The Fast Learning Algorithm for Deep Belief Nets. And that was basically the birthing point of deep learning. So that's a pretty big point in machine programming history.
All right, now with some of the people involved in advancing machine programming and machine learning and all that, one of the big ones is Justin Gottschalk. He's a founder of Merly AI, also a professor of computer science at UC Berkeley and Stanford. He also contributed, along with a couple of other researchers, to the three pillars of machine programming, which we'll go over in depth a little bit. He's also one of the head Intel AI and machine learning researchers. So yeah, he's kind of a big deal over there. And really, he's the one that's posted a lot of more of the papers regarding machine programming. He really is one of the top guys from that field. Similar with Armando Solar Lizama, he's a professor at MIT's computer department. And he has also composed many papers on machine learning as well as other topics in computer science. But specifically on machine learning, he's really worked on generative models and everything like that. On the other side, we have Greg Corrado, which is a senior research scientist for Google. And some of his areas of expertise include machine intelligence, machine perception, natural language processing, and distributed systems and parallel computing. Some of the organizations that have been involved in the creation of machine programming in these recent years have been Google, Intel, and MIT CSAL. AIL, my bad. So Google recently came out with AI pretty much to compete with ChatGPT called Bard. It's been recently released, and that's one of Google's biggest AIs for generative models. But they also have TensorFlow, and TensorFlow is really interesting because it's used for machine learning, but it allows its users to see flowing graphs, so they can visually get a representation of how their code is working and how it's being used in their businesses, which is actually something that is very interesting. Intel takes a little different approach than Google does in the terms of how to use AI. They use it more for hardware. So they're trying to automate programming on processors to make them both better and more efficient. Similar to how Julian said earlier, how Google AI made a better hardware than humans could. So Intel is on that route as well, making those advancements in those fields. And MIT is also has their own artificial intelligence lab, and they spend a lot of time researching, funding, and really just getting students exposed to all these type of ideas. And a lot of these papers that have been produced have come out from the MIT CSAIL program. All right, so these are just some of the sources that we've had so far. So now we're going to get into our first paper. So the first one is The Three Pillars of Machine Programming. This was published by the ACM Digital Library. It can also be found in other places, but it was published in June 18th, 2018. Here's our source right here. Some of the authors, Justin Gottschalk and Armando Solardazama, which are some of the people we talked about earlier, as well as Nassim Tatbul, Michael Carbon, Martin Renard, Regina Barzilay, Saman Amarasinj, Joshua B. Tenenbaum, and Tim Matson, most of them from which come from MIT and Intel. So some of the things that it goes into is as machine programming, machine learning, and artificial intelligence emerging, it is essential to have principles in which programmers could follow to develop these type of software. So these professors, these researchers went out and they pretty much laid the groundwork for three fundamentals when it comes to creating AI/ML, which is intention or understanding the human programmer's goals and expectations, invention, so taking past solutions or creating entirely new ones from the generative AI and all that, and adaptation, so the versatility when it comes to making solutions. Sometimes it needs to take one route instead of the other, and also how each one relates to each other. So this directly relates to machine programming as it's an exploration on the possibility of having these ideas as the groundwork for all machine programming and learning as it's going into the future. So here we have just a quick little diagram so we can see the three different foundations of making software that's self-reliant and everything. So we have invention, intention, adaptation, how they kind of overlap, and how data kind of just surrounds everything. So some of the results that they've seen is they just really set principles and ideas on how this could impact data in the future with the development of AI and machine learning. And they also went over some of the implementations in the fields of natural language processing specifically. And that's everything I've got about this paper.
All right, my paper was titled Machine Programming, Turning Data into Programmer Productivity. It was also published by the ACM Digital Library just last year in 2022. And the authors are some very familiar faces that we've already talked about in this paper, at least, I mean, in the slides, at least Justin Gottschlich is, as well as Nassime Tatbul and Abdul Wasay. All right, most of this paper just kind of goes over the current state of machine programming and also where it's going in the future and some of the advancements it's already made. But to start off, it kind of talks about the data part of machine programming, which is very important. Specifically, the data sources. We get the data for machine programming and AI and things like that from code repositories. Think GitHub, documentation, telemetry data, which is kind of like, system diagnostic data, things like that. Incomplete and synthetic code, plus natural language. That could be things like Stack Overflow, leak code, forums, all of that data. And also open research, any type of paper in the ACM Digital Library or any other library on the internet. It also talks about some of the advances that machine programming has already made, specifically in general systems and also data-intensive systems. Coding interfaces is one thing that has been advanced significantly in the past few years. Here on the right, we see the logo for Thunkable, which is a kind of a no-code mobile app builder. So those type of applications have been rising in the past few years because of machine programming. Code intelligence, like GitHub Copilot, which we talked about before. There's also, IntelliSense that Microsoft makes. And also debugging, automatic debugging code. GitHub Copilot can debug your code, a lot of things like that. There's also data flow systems, which is just applications that require both data and code. So those go hand in hand, and that has been advanced in the past few years. Cloud microservices, think AWS, all of those have been, they've increased their efficiency and things like that because of machine programming. And then data science pipelines. So data science is a really big field. And there's actually this one program called Snorkel that we can see here, the picture of the logo, that uses AI and machine programming to actually label unlabeled data. So, data is very important, and having unlabeled data isn't useful at all. So having that data be labeled very quickly by machine programming is extremely helpful.
All right. Some of the impacts that machine programming can have in software development, hardware development, and cybersecurity are some of the following. So, in terms of software development, more efficient code can be made as does not have to be replicated in each programming language, as well as new code released from the algorithms could be used from using previous code. And databases are also readily available for ML to use. So, in the case of Intel, they have all their code database, all their repositories, and everything. AI could simply go into there, look at examples, and bring out brand new code. In terms of hardware development, so development could be aided by machine programming to create more efficient hardware, and newer processors such as heterogeneous and neuromorphic processors can require large amounts of programming. So ML would be one solution to do it faster than any human would. Again, going back to that AI being faster than humans example. And in the terms of cybersecurity, AI does things a lot more faster and a lot more efficient. So being able to find vulnerabilities and security breaches will be helpful in mitigating the attacks and risk of being breached. So that would definitely help white hat hackers as well. And as well as the automatic recognition of vulnerabilities and threats in quote, making anything that could potentially be exploited be secure in a matter of seconds. All right, so these are just some of the impacts, and this has been our project. Thank you very much.